Welcome everybody to our first look at power series. So in our discussion of power series, probably the best thing to do is really answer a question as what is a power series? Well, kind of we want to think of power series maybe as generalizing polynomials. And when we say generalizing polynomials, basically we are saying, let's let the degree of the polynomial go to infinity. So really we have a function that's going to be a function of the form sum n equal to 0 up to infinity of a sub n x to the n. And so in this case, this thing really looks like a0 plus a1 times x plus a2 times x squared plus ... And so we do have something that looks like an infinite degree polynomial. It really is kind of a generalization of our polynomials. In fact, we can really think of our polynomials as being a special case of a power series. That if somebody just gives us a polynomial that happens to be of the form, let's say 2/3 plus 4x plus 5x squared, well, we can think of this thing as being a power series where after the second degree, we really just have all of our coefficients are just going to be zeros at that point. So our polynomials are really kind of special cases of our power series. Now, from this perspective, kind of thinking of these as being generalizations of polynomials, it really kind of makes it a little easier to see what might be a power series and what might not be a power series. So if somebody just gives us an expression like this and says is 2 plus 6x plus 12x squared plus really written in the form of an infinite series like this, is this going to be a power series? Well, yeah, if we look at the powers on all of the x's, this really does look like a generalized polynomial. And so in this case, we really do have a power series. So is this one a power series? Yes, it is. So what if somebody gives us this expression and says, is this going to be a power series? Well, in looking at this one, we're seeing we have a sine of x, a sine of x, a sine of x. We have something that's a transcendental function of x. So we've got a transcendental function of x, so that thing in and of itself is not going to be a polynomial. And that then prohibits this from being a power series. So is this one going to be a power series? No, it's not. The sine of x kind of messes that up. So what about this third example? Will this be a power series? Well, again, if we look at kind of the powers on x, we have this square root of x that's showing up in here. And so this thing really looks like a square root of x times an infinite series. Well, in this case, will this one be a power series? Well, the answer again is going to be no in this case. So here again, if we're asked if this is going to be a power series, well, we're looking at the powers that show up on x. We have x to the -1, x to the -2, x to the -3. Any x to non-positive integer powers is not going to look like a generalized polynomial. It's not going to look like any kind of polynomial. And so is this actually going to be a power series? Well, again, the answer would be no, it's not a power series. So finally, if we look at this expression, we see a power of x, we see a power of x cubed, we see a power of x to the fifth. All of our powers of x are going to be positive integers, and so in this case, this does look like a polynomial in that respect, and so in this case, an infinite degree polynomial. So in this case, yes, we do have a power series in this case. So a couple of other things to kind of round out this first discussion of power series is really talking about the center and the radius of a power series. So when we're talking about the center of the power series, the examples that we've seen so far have all been centered at 0. But basically the center of the power series, n equals 0 up to infinity of c sub n, we're really looking at kind of what's going to be one of these zeros. So if we have c sub n x minus a to the n power, this is going to be a power series. And for this power series, we say that it is centered at x equal to a. Now, why do we say necessarily that it's centered at a? Well, now comes in looking at the radius of a power series. We want this series to converge to some value, and so what do? We turn to the ratio test to tell us when these things will converge. Now, for the ratio test, remember that we're looking at the limit as n goes off to infinity of the absolute value of a sub n plus 1 over a sub n when we're given this infinite series. Well, in this case, we have the limit as n goes off to infinity of the absolute value of c sub n times x minus a, c sub n plus 1, x sub a to the n plus 1, over c sub n times x minus a to the n power. So if we go through and we kind of simplify this just a little bit, let's take a look at what happens. So we can cancel our powers of x minus a to the n. So we really have something that looks like the limit as n goes off to infinity of c, the absolute value of c sub n plus 1 over c sub n times the absolute value of x minus a. Well, the x minus a doesn't have any dependence on n whatsoever, so we can actually pull that out of our limit. And so we have the absolute value of x minus a times the limit as n goes off to infinity of c sub n plus 1 over c sub n. So now kind of coming back to our usual ratio test, this is really what we had whenever we said that this was going to be some value of rho. So when our series was going to converge, so remember that the ratio test gave us absolute convergence when these values were going to be in between 0 and 1. So whenever we had the absolute value of x minus a times rho going to be in between, we're going to be less than 1. And so what happens now in this case, we really have an expression that looks like this. So the absolute value of x minus a is less than or equal to 1 over rho. It's this 1 over rho that we end up calling the radius of our power series. So this 1 over rho, this is the radius. And so we have an interval of x values that has a certain distance away, and so we end up with an interval of convergence. We end up with an interval of convergence that looks something like, we have our value of a, we have an interval here, we're going out a distance of r in that interval, and so this gives us an interval of convergence. And so where do we get the notion of the center of A? Well, our value of A is right in the center of our interval of convergence. And so we can talk about the center of the interval, and we can talk about the radius of the interval. So this kind of looks like an open set centered at A going out to some distance. Now there is kind of possibilities that our radius could be 0. So kind of from the ratio test, we know what can happen, that namely if our 1 over rho equal to r could be 0, in which case the only value that works is x is equal to a. So we could have a radius of 0. We could have some finite value, or we could have the possibility where our radius is actually infinity, in which case there we get an interval of convergence of the entire real number line. So we could have a single value as being our radius. We could have a radius that looks like a minus r out to a plus r in the finite value case, or we could have an infinite radius and our function actually converges for any possible x value that we want to put into that function. And so this kind of gives us this notion of power series generalizing our polynomials, but it opens us up to a much broader class of functions at that point, and actually what will turn out to be an incredibly useful class of functions. So I hope you've enjoyed this, and I will see you guys next time.